Hey. Hey, everyone. How's it going?
Okay. Sounds good at the back there. Good morning, everybody. Did everybody have a good night? No? Everybody's a little hungover, maybe? Well, yeah, I'll take by your silence. Y'all had a little bit too much to drink, but there's lots of free coffee, so make sure you get your fill of that. This morning, we have a great talk by Willy here on exploiting vulnerabilities in H.264. First talk of the day, kick us off. So thank you very much.
Awesome. Thank you. Hey, everyone. Thanks. I'm very excited to be here. First time at REcon, so let's go. Yeah. We'll be finding and exploiting vulnerabilities in H.264 decoders. This is joint work with Stephen Checkaway of Oberlin College and Hobaf Shisham of UT Austin. Bit about myself, I'm Willy Vasquez. I go by Werv. I'm a PhD student at UT Austin. I do research in system security, cryptography, and cyber law and policy. Previously, I was at MIT and BBN, and you can check out my website with more adventures I get into. The roadmap for today's talk is that first, we'll be talking about the decoder attack surface, as well as the complexity of video decoding. And then I'll explain how we're able to tame that complexity with our tool called H.264, or domain-specific infrastructure to modify encoded videos. And then I'll show you how to use the tool by providing an expanded root cause analysis of an Apple in the wild 0-day, CVE 2022-22675. And so the main takeaway I want you to have from this talk is that with H.264, the complexity of working with encoded videos is reduced, unlocking a new attack surface. And something to note is that this work will appear at Usenix Security. The paper is out. You can check it out at that link and get some spoilers. So let's dive right into the video attack surface. So video is everywhere. As you're just scrolling the web, videos will autoplay. As you're messaging your friends, you'll share funny videos with each other. And something to note here is that even video thumbnailing touches the video decoder. So what this pipeline looks like is you'll get an MP4 file, which is a container format that has the encoded video itself inside. And your browser or video player will parse the MP4 metadata and forward along the encoded video to a kernel driver, which will then parse these parameter sets, I'll describe them later, in order to prepare the hardware to take the compressed frames and produce each individual frame that you see. So why do we need this dedicated hardware decoding? It's because decoding is computationally heavy, and we want dedicated hardware to ensure a smooth playback. In fact, in our work, we found over 25 different providers of H.264 decoder intellectual property, or IP, and there's likely even more than this amount. And each video decoder has its own kernel driver that controls it. What this kernel driver is doing is it's taking untrusted input from the internet, it's parsing it, and then it's sending it off to the hardware to produce frames. Surely nothing could go wrong. So let me tell you about the Apple mobile hardware video decoder and what can go wrong. As far as we're aware, the iPhones have had two different decode IP. First, the Apple D5500 is found in A11 SoCs. It's created by Imagination Technologies, and you'll find other phones that also have this D5500 out there. Later in the Apple A12, as well as M1 Max, they introduced Apple AVD, which, as far as we're aware, is their own internal IP. And each of these have their own kernel drivers or kernel extensions, KEXT. So surely nothing can go wrong here. No. we were, in the course of this work, we were able to find 3 parsing vulnerabilities in the Apple D5500, 2 of them being zero-click. And in fact, as I mentioned earlier, there was this in the wild Apple AVD H.264 vulnerability being exploited. And for this talk, we'll be focusing on building upon the existing root cause analysis in order to get I'll show you how to get a heap overflow using this bug. So before we talk about the vulnerability, let me tell you a little bit about the H.264 codec itself. H.264, or the Advanced Video Codec, AVC, was standardized in 2003 by two different groups, the ITU and MPEG. And so because of this reason, it has two different names, H.264 and AVC. But we're going to be sticking to H.264 for this talk. And the spec itself is over 800 pages describing video decoding. So even though it was originally standardized in 2003, it has been updated every couple of years. You can see from the screenshot that this is from August of 2021. And what makes H.264 interesting is that it's supported on practically all modern devices. And in fact, it's considered the fallback codec for video engineers because they expect almost every device to recover it. So the language that H.264 uses to describe videos is what are called syntax elements. And inside of the spec itself, it's shown in this pseudocode-like fashion that describes the direction for decoding, as well as the bitstream representation, or the entropy encoding for each syntax element. And accompanying each syntax element is what are called the semantics. The semantics describe what each syntax element does, as well as the expected range that it should take on. And we can see in the syntax that these two work hand in hand. Depending on if this chroma format IDC is equal to 3, it'll parse the bitstream differently. I also want to note here that for the remainder of this talk, orange dash boxes are syntax elements, blue dotted are semantics, just for your own info. So what we want to do in our work is generate syntactically correct, meaning that the bitstream is decoded correctly, but semantically non-compliant videos where our syntax elements are out of bounds. So to show you what can go wrong with this bitstream representation, here we have the opening sequence from last year's REcon talks available on YouTube, and here's a portion of the bitstream of it. And suppose we take this 72 and we just increment it to 73, and now we get this kind of cascading effect. And let's increment it one more time, 74, and we get this fun rainbow color. Happy Pride. So these bitstream representations, they can have they can lead to security issues. And in fact, other folks have also identified security problems in codecs. In fact, Donenfeld looked at Apple D5500 and has a Hack in the Box talk, as well as a FRAC article. Gong looked at the Qualcomm Venus hardware video decoder. Last fall at Hexacon, Tarakanov and Labunets looked at Apple AVD, and Natalie Silvanovich has also looked at Apple AVD and found many bugs. Relevant to us is this in the wild vulnerability that was looked at researchers Binary Boy and Little Lilo, as well as Natalie Silvanovich herself. So let me now explain what this issue was. So this is an in the wild Apple AVD H.264 kernel vulnerability. It was patched in macOS 12.3.1 and iOS 15.4.1. And it is a missing bounds check for this CBB count -1 syntax element. And this value is used immediately after as a loop bound to write into an array. It is entropy encoded, and its expected semantics say that it should be within the range of 0 to 31. So from this missing bounds check, what we want to do is set this syntax element to its maximum possible value and ideally get a crash. The reality is that this setting this value is a very painful experience. In fact, Natalie Silvanovich herself describes having to forge the file bit by bit, setting up FFmpeg inside of a debugger and just creating the file this way. And Little Lilo and Binary Boy also describe their challenges. And the exact issue here is the bit level granularity of entropy encoding. So the CBB count -1 value, it's always an odd number of bits. And so it's not enough to just pop it in a hex editor and modify things. Furthermore, it depends, there are syntax elements that depend on it. So every time you increment it, you have to update the bit stream in order to modify the dependent values. So doing this by hand at scale is infeasible. And even though it is possible, it is quite challenging. The lack of tooling is holding back security professionals. So to summarize this part of the decoder attack surface, just three main things you all need to take away is that video decoding, including thumbnailing, is done in kernel drivers and dedicated hardware. The syntax elements have semantics, but those are not always enforced, as we saw in this in the wild CVE. And furthermore, modifying the syntax elements is possible, but currently a very challenging process. So let me now describe our tool that we created, H26 Forge, where now modifying syntax elements can be done with just a few lines of Python. Here's the previously it was a pain, and now setting the out of bounds CBB count -1 is just here. And furthermore, the dependent values are also updated. How this works is that we've created this tool and 30,000 lines of Rust that will essentially abstract out the bitstream representation or the entropy decoding and encoding. And what it focuses on is loading up the syntax elements into memory where they can be programmatically modified with Python scripts. Similarly, we can set them to any random value in order to generate videos at different kinds of outputs. So we can produce MP4s, encoded bit streams, or any other outputs for different contexts. So this video generation procedure is the same. Here's the same CBB count -1. We just pass in a JSON configuration for the range of each syntax element. And we also get funny looking videos like this sometimes. So with our video generation, we were able to find vulnerabilities in video players, kernel extensions, and hardware. In Firefox, we have this out-of-bounds read vulnerability, and we also found some issues in hardware. And the details of that are in our paper. For now, we'll continue to look at the expanded root cause analysis. We'll continue by looking at this Apple O-Day that was in the wild. Again, why we think this is valuable as a case study is that it's an in the wild Apple kernel day. That's wild. Furthermore, we think it well demonstrates the complexity of the H.264 spec, as well as shows the capability of our tool, H26 Forge. So what Apple AVD does is it creates this user context that maintains the recovered syntax elements in memory, along with other playback information. And CBB count -1 and its dependent values are stored in SPS, which I'll describe in a bit. And with this out-of-bounds value, we can get an 832-byte overwrite outside the bounds of the SPS. So the SPS stands for sequence parameter set. This is basically the frame size and frame rate of the video, and the user context has an array of 32 SPSs. The picture parameter set, or PPS, describes the compression information for compression details for each frame, and we have an array of 256. And these are both used to set up the hardware decoder. So we have this 832-byte overwrite. We have an SPS that is a little over 2,000 bytes, and a PPS that's 600 bytes. So with our overwrite, we can overwrite a neighboring SPS or completely overwrite a PPS. So this that I've described was already known. Here is a screenshot from the root cause analysis, where we can see that we can overflow into other members of the decoder struct. But even with this knowledge, it was difficult to find a proof of concept media file that crashed the system, meaning that the condition that allowed this exploit to live out in the wild was probably quite subtle. And here we answer affirmatively that yes, this is very subtle. There's a lot of dependencies going on. So now I'll be describing an exploitation strategy in order to get us a heap overflow. I want to remind y'all that as far as we're aware, we don't know how it was exploited in the wild. If anyone here knows, I'm happy to chat. So in creating our exploit strategy, this analysis was done in iOS 15.4, and we used three main tools: Ghidra for kernel reversing, Corellium for kernel debugging, and H.26 Forge to produce our proof of concept video. So the key idea here in our exploit strategy is to take advantage of syntax element dependencies to trigger a second larger heap overflow. So first, we have the vulnerability in our SPS, and we'll be able to write over these arrays. We're going to use that in order to overwrite a PPS, specifically this number of reference indices value. This value should only be in the range from 0 to 31, but we'll overwrite it to be out of bounds. This value is used in slice decoding. A slice is the encoded frame that the hardware works with. And in this function, prediction weight table, it's used as a loop bound itself. So we will be overflowing these parameters in order to get a panic. In order to get there, we're going to have to overcome three challenges. First, we'll have to construct the bit stream so that it's actually using the values that we are overriding. Second, this loop I'll show you in a bit. We need to have it become a larger overflow, and then third, we'll have to figure out how to control where we write. So diving into the first challenge. Each SPS and PPS has its own unique ID that acts as an index into the array. So we decode an SPS and PPS with ID 0 so that they're now in memory. So that's part one. Then we decode an SPS at index 31 that will then overflow into use the overflowing HRDs in order to overwrite a PPS. And we're going for this number of reference indices value. Reminder, this should be within the range of 0 to 31. And in fact, whenever the Apple AVD is decoding this syntax element, it actually does this check. It saves the value, and then it says if it's greater than 31, it'll print out an error and stop decoding. But because it's already been parsed, and now we're overwriting the value in memory, we have a time of check, time of use issue. So how we actually construct this bit stream, and here I'll be showing Python snippets that we use in our tool. These are just a collection of flags in order to get to the actual CPP count -1 overwrite. And here is where we're actually writing our payload. And some things that I want to point out here is that we're overflowing this array in order to overwrite a neighboring struct, meaning that there are some dependencies that we need to be maintained. So like this entropy coding flag, we can just set it to true here in our script. And this weighted prediction flag, we can just reference an already decoded syntax element when constructing our payload. So all this gets nice and packaged up to the CPP size value -1, which is inside of the parse HRD or overflow. One thing that I want to point out here is that this number of reference indices that we'll be writing into is a byte value. So the max value that we can set it to is OXFF, 255. And we'll come back to that in a bit. So now that we've constructed our SPS, we override it, we've modified it in memory, and now we actually want to use it. So decoding each slice, Here, I'm just going to update the picture to show you that the user context has an array of 600 slices. And this is the number of reference indices. So first we decode a reference picture, and then we decode a slice that will actually use our value. And here, the number of reference indices that's used, there's this overwrite flag that if it's set, it'll overwrite the value there. But if it's not, then it'll use the default value, the one that we've already overwritten. So we just set that flag to false. We don't want to override our value in memory. And whenever encoding the video, we set it to our overwritten value, OXFF. So now that our slice has the out-of-bounds value loaded up in memory, we want to use it as here in this loop bound. So we've set it to 255, and so it's going to loop over in this array, which should only be 32. So now we're going to be overriding into our own slice context, and we can write at most 512 bytes from the start of the furthest array object. So here, each slice struct is around 12 kilobytes. So since we can only write 512 bytes, we'll expect it to only write a portion of it, but that's okay. Let's just do it and see what happens. We see that we get a panic. We were expecting the small overwrite, but we end up getting this panic. When looking at the disassembly, it turns out that whenever the number reference indices is loaded, it uses this instruction, load RSB. And this signs extends that byte to 32 bits. So now our OXFF becomes OXFFFF. So now this is looping practically infinitely, and it's going until it runs out of memory. So the question is, can we control this? Can we get the kernel to stop early? So looking back at this prediction weight table, now our number of reference indices, we're looping at this 4 billion times. But each time, it's parsing these luma chroma weights and offsets. And according to the spec, each one should be in the range of -128 to 127, which Apple, the AVD, correctly checks. It'll first write the value into memory, and then it'll check if it's out of bounds and exit if so. So that means that all we have to do is write an out-of-bounds luma chroma weight or offset at whatever target we want, and we're good. So now we can write at at some whatever offset that we want. Something that I want to point out here is that memory up to our target is modified. This is because, according to the semantics, when when the flag is not set, it'll write this default value. But it's not issued because we can just enable this flag and write any inbounds value that we want up to our target. How we constructed the video to produce this is that even though the PPS loop bound is OXFFF, we can calculate the exact number of reference indices that we'll need to our target. So here, with some reversing, we calculate the number that we need, we set it to the slice, we set some default values, and finally we write down our target. We put down the target value that we're writing. So we'll be writing OX4141 there. And we can see here that there's our OX4141. So we did it. We were able to get a panic using this vulnerability. But wait, there's more. So looking back at this code snippet where our out-of-bounds value is written, this goto, it doesn't stop the decoder. In fact, what it does is that it just continues on to the next slice. So we can just do the same trick again. So now we have our first write, and for each subsequent slice, we just do the same thing and write whatever arbitrary value that we want in chunks of uint16. And so now as we decode each frame, we're essentially writing our value backwards. If you're interested in seeing what the complete proof of concept looks like, it's in the appendix of our paper. And now here's a demo showing how to get the panic on Corellium. So here I've set up an iPhone SE with 15.4. This is a web page that has the attacking context. This is the one that will be overriding into a vulnerable context. And so the attacking context is set to autoplay, so it'll automatically load it into memory. And what we first do is play this, the vulnerable context. Also, I need to talk with the Corellium folks here. None of my videos play. I don't know why. This should be a good video. So, but the vulnerable context is played. It shows up. And now we play our attacking video that is overriding the vulnerable context. And once we play the vulnerable one again, we get a crash, a panic. And here we wrote deadbeef, got modified a bit, but that address was dereferenced, and our PC is now this junk. Ah. So where do we go from here? So we've shown you that we can write inside of our user context or also a neighboring user context. On iOS, the first member is actually a packed vtable. So we'd need a pointer authentication bypass in order to actually escalate from here. And in this talk from Hexacon, Tarakonov, and Labunets suggest smashing other pointers in the neighboring context and winning some race condition when the user context is used. If anyone's familiar with how to do this, I'm happy to chat and figure out how to create a proof of concept. So now I've described to you the decoder attack surface, that it goes all the way down to the kernel. I've shown you our tool, H26Forge, and I've shown you how to use it to understand this in the wild Apple zero-day vulnerability. So with H26Forge, the complexity of working with encoded videos is reduced, unlocking a new attack surface. And again, with this tool, we can create syntactically correct, but semantically non-compliant H.264 videos. The code is still being cleaned up. It'll be available at this GitHub link by August, where this work is presented at Usenix Security. If you want more information, you can check out our paper as well. And I'm happy to take any questions now. If you have questions, raise your hand. A mic will be brought towards you.
Hi. Hello. So I was wondering, just for the existing landscape of known H.264 codec vulnerabilities, how many of those are memory safety issues, kind of at their root?
I'm sorry, how many of those are?
How many of those end up being memory safety issues, rather than, say, logic issues?
We found one denial of service issue. I think most that we found are end up being memory safety that arise from logic-related bugs, not just missing bounce checks.
Thank you.
All right, cool. Well, thanks everyone. I'll be around.